So, welcome to the closing keynotes. Did you have a good time already? So, I can only give you one tip. Don't talk about DevOps to your friends or colleagues. Just say it was really bad. So that way you have more chance to get a ticket next year, right? So that's the deal. Anyway, so I'm really happy. Well, I'm happy for two reasons. This is going to be a great closing keynote. I've seen Dylan perform this talk at DevOps UK, and when I saw that talk, I was like, oh, I need to invite him to Belgium. And he was really happy and keen to do this, so I'm really thankful. Thank you for that.
Always welcome.
Great.
Normally I have to drink English beer, so.
Yeah, watch out. I told that in the opening keynote. Belgian beer has more alcohol, so you have to watch out. And the second thing I'm happy about is it's the fourth day. Well, it's the fifth day for us, so it's like, if you get a bit older, the battery actually goes to zero a bit faster. So we're almost there as a team, and I would like to thank the team. And it's been an amazing journey. So yeah, cool. And practically, so after this keynote, which will take 50 minutes, not 45, but you can then go to the other room, which is room 8. There we will have popcorn, and then at 8 o'clock we'll start the movie Top Gun. And I've asked them at 56 minutes that they would freeze it for like 5 seconds as well. So it's really realistic and in sync with my keynote. Cool. Anyway, Dylan, it's all yours, man.
Thank you. Hello, everybody. I'm Dylan Beattie, and the first computer that I ever owned was one of these, the Amstrad CPC 6128. Some of you might know that as the Schneider 6128, where it was sold in Germany and the Netherlands, and some of you have never heard of it, because this was an 8-bit computer from the 1980s, and it was not very good. It came with a chess game that was not very good, and a flying game that was not a patch on Top Gun Maverick, no matter how hard you tried. But it came with a programming language called Logo. And when I discovered Logo, I realized I could make the computer draw pictures. Now this was a big deal in 1985, I was sort of 7, 8 years old, and we weren't used to seeing pictures on computer screens, because computers only did text and numbers and spreadsheets and boring stuff, and I could make it draw pictures, and I could make it draw shapes, and I got obsessed with this. I got hooked because I loved the idea that by writing commands and running programs, and I didn't know what they were I knew what I thought they were gonna do, but I would run them to find out if I was right. And that process of typing commands into the machine and pushing go and pushing run and seeing what came out the other end of it, I got hooked on that when I was 7, and I have never looked back. I am still hooked on doing that to this day. And this talk is all about the ways in which we have used computers and technology to explore and understand the world around us. So this is my Schneider one, my Amstrad 128, and I was using this to make art. And you've probably seen a whole bunch of talks here at DevOps about coordination and container orchestration and security, stuff which is useful, stuff which is valid and relevant. The learning ends here. It's been the end of a long day. You're not going to learn any more useful stuff. You are going to learn about art, and art is useless, says Oscar Wilde. All art is quite useless, because if it was useful, it wouldn't be art. It would be something useful that happens to look nice. But there's another quote about art which I like, which is Douglas Adams paraphrasing Shakespeare. And he said, "The function of art is to hold a mirror up to nature. And if we want to do that, first we have to invent the mirror. And that is where science and technology and engineering come in. Because we have built machines that have allowed us to explore and understand things that have been there the whole time. But until we had the technology to play around and experience them, we had no idea." This photograph is silica crystals on the eyelid of a beetle, taken through a scanning electron microscope. They've been there the whole time. But we had no idea that this kind of beauty was lurking there. This is crystals of salt growing in a dish of soy sauce. This is the fronds inside one stem of a banana leaf, all taken using scanning electron microscopes. And we have sent spacecraft and cameras and people into space. We photographed Earth from the far side of the moon. We photographed our solar system, the pale blue dot here, in the rings of Saturn. This is us down there. That's planet Earth from the other side of Saturn. And by the way, this photograph was taken using a tape deck. I only found that out last week because Voyager, the satellite that took it, didn't have a disk drive because they hadn't invented them yet when they launched it. And we've taken photographs like this one. This is from the Hubble Space Telescope. It's a thing called the Eagle Nebula, the Pillars of Creation, 7,000 light years away. Now, in July this year, some of you probably remember this photograph making headlines. This was the first image from the James Webb Space Telescope. Now, I want you to imagine taking like a 19-inch monitor like this one, and you put that in front of you on your desk, and then you're like, I want more screens. And you put another one there, there, and then you're like, I can put some up here. Until you are inside a globe of monitors, all about 1 meter away from your eye. There are this many stars behind every pixel. This is an area of sky equal to a grain of sand held at arm's length. And we have the technology to photograph that with this kind of definition. It is absolutely astonishing. But within my lifetime, we have started using technology to explore another hidden world that has been hiding under our noses all of this time, a world of mathematics and information. What is the area of that square? 2 by 2. It's all right, it's not a trick, it's 4, yeah. So if we now draw a square which is -2 by -2, what's the area of that square? 4. Also 4. So how do we make a square whose area is -4? And reality says, you can't, it's impossible. And maths goes, hey, hold my beer. That's all right, this is maths. We can do anything we like. Yeah, let's just, we imagine the number. The imaginary number I is the square root of -1. And reality goes, you can't do that. And maths goes, yeah, we can do anything we want. We have maths. As long as we are consistent or correct, and sometimes both, that's fine. Now, these complex numbers which have a part that is real and a part that is imaginary, they are often drawn on graphs like this. This is the complex plane. We've got a number here. It's 0.8 of real stuff and 1.2 of imaginary stuff. That's what this number here is. And we can do maths with these as long as we remember. So we have 0.8 plus 1.2i. We want to square this. So we say, all right, we'll expand the brackets just like back in high school, and we'll multiply all the bits together. And all we need to remember is anytime we get I times I, it flips to be negative. And so we expand it out till we got the blue bits and the red bits. We simplify it all down. We can do maths with complex numbers. Now, the first person, or the first people to really study this were 2 French mathematicians around 1917, 1918, Gaston Julier and Pierre Fatou. And I have not read their paper because it is 125 pages long and it is in French. But I've read lots of books written by people who did read their paper. And what they were studying, this is their memoir on the iteration of rational functions. And they were interested in how do mathematical functions behave when you iterate them. Now, if you take x goes to x plus 1, you can just see that's going to go 1, 2, 3, and off it's going to go. If we say x goes to 2 minus x, well, 2 minus 0 is 2. 2 minus 2 is 0. 2 minus 0 is 2. 2 minus 2 is 0. This has stable behavior. We can see within a couple of iterations, yeah, we know what's going to happen. If we say x goes to x squared, well, 2 goes to 4, 4 goes to 16, 16 goes to 256, and off we go. And if we say x goes to x squared and we start below 1, we get smaller and smaller, and we asymptotically approach 0. We never get to 0, but we approach it. We keep moving towards it. Now, we're going to take this number, and we are going to iterate this complex number by just squaring it. We're going to say z maps onto z squared. So it starts off here, and we square it, and it goes over here. And we square it again, and it ends up over here. We square it again, and it pings back up to there, and then we square it again, and it disappears off to one of the 4 infinities, because there's a positive and a negative real infinity, and a positive and a real complex infinity on this graph. So what we're going to do now, we're going to take another point, which is almost the same place. We're going to take this one here. We're going to iterate that. We're going to start this point, which is just next to it. That one vanishes off to positive real infinity. This one goes off to imaginary infinity. Now we're going to take a point next to it. Now this one kind of hangs around for a bit. and it bounces around the middle. At one point, it looks like maybe it's decided it's going to be a circle, and it bounces around a little bit, and eventually it gets bored, and it's like, yeah, you know what? I'm fed up with this. I'm off. Infinity's looking pretty good to me right now, and any second now, off it goes. There it is, and it's gone. After something like 45 iterations. This one here, boing, 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 and it disappears down the hole in the middle of mathematics. Now, these points are almost next to each other. They differ by 0.1 on the real axis, but they exhibit this dramatically different behavior, iterated under the simple, just keep squaring it, squaring it, squaring it. And the first person who really studied this particular phenomenon was this guy, Benoit Mandelbrote. He was a Polish, French-American mathematician. He had like the best job ever. Like, he worked at IBM. He worked at the Thomas J. Watson Research Center when they had a computer, and there were only like 6 in the world. And when he got bored of computers, he went to Harvard, and he taught mathematics. And then when he got bored of that, he would go back to TJW, and he'd play with the computers again. And he was fascinated by the geometry of nature. He had this famous quote, "Clouds are not spheres, mountains are not cones, coastlines are not circles, bark is not smooth, lightning does not travel in a straight line." Now, his great insight, the thing which bears his name to this day, was if you take a point in this plane, you can iterate it and add it to itself. So z goes to z squared plus the number you started with, c. Any point in this plane. Now, he and his team, they had computers. Gaston Julia and Pierre Fatou, they had to do this with pencils and paper. Mandelbrot had computers. They were primitive computers. They were just about smart enough that they could divide their 80-column line printer into squares, and they could say for each square, iterate this thing 100 times, and if it hasn't gone to infinity, draw an asterisk. That was their algorithm. Take each square on the grid, iterate, and if after 100 times it's not infinite, draw an asterisk there. And they printed this. They were the first people in history to see the Mandelbrot set. Now, we invented mathematics and floating point coprocessors and high-definition color displays and color printers and all kinds of cool stuff. And the algorithm we normally use today is that when we draw the Mandelbrot set, we color-code it based on how quickly it goes to infinity. If it goes to infinity straight away, it's blue. If it goes a little slower, it's purple. If it takes a long time, it's red. And if it still hasn't gone after 100 loops, we paint it in black. And that is very simplified how we draw these kinds of images. But of course, we have the computing power to draw this at a much finer level of detail. We can take an image like this one, the Mandelbrot set. Now, what I'm actually going to do is we're going to start from here, and we're going to start zooming in. This is the Mandelbrot deep zoom. So we're going to say that that's magnification factor 1 around about now. So we're going to go 2, 3, 4, 5. We're going to keep zooming in. Around about now, we're at factor 10. So the original shape is it's kind of the size of this room at this point. And we're going to keep zooming in. And we're going to keep zooming in. And we're going to keep zooming in until the original shape is the size of Antwerp. And we're going to keep going, and I reckon round about here, the original shape is probably the size of Belgium. And we're going to keep zooming until our original shape is the size of mainland Europe, the size of planet Earth, the size of the solar system. It's going to keep, and we are never, ever going to run out of detail. Because inside z goes to z squared plus c, if you have a fast enough computer to explore it, there is an infinity of detail and color and beauty and self-similarity. This is not a replica of the shape we started with. This is an echo of the shape we started with. And if we kept on zooming in until our original shape was bigger than the known universe, we'd find there were still more details there that nobody had ever seen before. Now, we have used computers to explore these kind of mathematical shapes. We've also worked out how to use computers as tools. We have worked out how to use computers in Hollywood and advertising and photography. In 1982, this movie came out, Tron. It was funded by Disney. It was produced and distributed by Disney. It wasn't made by Disney because Disney's animators refused to work on it. They boycotted it because they said computer graphics were a threat to the field of animation, and it was disqualified from the Academy Awards because they said using computers to make movies was cheating. They eventually changed their mind on that one, and they gave it a Lifetime Achievement Award. 1985, the same year I was playing around with my Amstrad, we had Luxo Jr., the first completely cinematic, computer-generated movie. We had the Jurassic Park dinosaurs, 94. A couple of years ago, we had this guy. Now, who is this? Is this Peter Cushing, who's a dead actor? Or is this Grand Moff Tarkin, who is a fictional character owned by Lucasfilm Limited? You know, computers are raising all kinds of interesting questions about art and copyright and ownership, but they're also allowing us to answer important questions like, what if we remade Friends, but we put Nick Cage in all the roles?
Boy, that was terrific.
Really bitchin'.
Now, the way we do that kind of stuff, this is deep fakes. This is you take someone's face and you map it onto a piece of footage or something from somewhere else. And the tool that we use to do this is something called a convolutional neural network. And it's basically us attempting to emulate the way the vision systems in the human brain work. And teach a computer, train a computer, program a computer. We're not even really sure how to refer to what we're doing here. But what we are trying to do is take machines that can look at shapes and go, yeah, that cloud there, just like when you're lying in a field on a sunny day, you're like, yeah, that cloud looks like a rabbit. It looks like a cat, and that one looks like my bank statement. And your brain is filling in all these details. And the way we do it is we take a whole bunch of layers of self-reinforcing and filtering logic, and we train them. We don't tell them what to do. We give them a bunch of labeled inputs. We say, hey, these are cats, these are dogs, you figure it out. And a couple of thousand lines of probably Python code runs around and goes, right, got it. I think I can tell the difference. Which might not sound like a big deal. You know, cats and dogs are pretty different. But what about if we're trying to classify the difference between a puppy and a muffin? Easy? Now, the people working on image classification, they are doing important, serious work with all kinds of applications in, facial recognition, image analysis, autonomous vehicles. But then there's people like me. And when we see that somebody out there has created an automatic dog detector, what we do is we go, hey, let's wire that in backwards. So I took this picture earlier of the Kinepolis, a lot earlier because the sun was shining that day. And I ran it through the dog detection algorithm. It said there aren't any dogs in here, so I wired it in backwards and I said, crank up the power. The dog detector is now a dog amplifier. And the computer goes, this is a horrible idea. And I say, no, it's not. Increase the power. And the computer goes, please don't. And I say, come on. Maximum dog amplification. And the routine is going, this is horrible. You're going to have nightmares. I'm like, I don't care. Crank it all the way up. Maximum dog amplification. And we end up with things like this, these kind of images. Now, is this art? Because it wasn't created by an artist, or was it? We don't know. We don't really have the vocabulary to work out what these kind of things are. But it is a completely new form of expression, these weird, psychedelic, dreamlike images. It's called deep dreaming. Deep Dream was the project at Google where they originally wired the dog detector in backwards and came up with this kind of stuff. So we have come up with all kinds of amazing ways to use computers and technology to create art, to create pictures, to create movies, to create music. But what about if the code is art? Now, this is Donald Knuth's famous book, The Art of Computer Programming. And I'm sure many of you can relate to this experience, where you're reviewing some code late at night, and maybe it's somebody on your team, or maybe it's some code you wrote last week when you were tired and a little bit stressed, and you're looking at the code and you're thinking, I don't know what this is, but it's not art, it's not science, it's not engineering. I don't like it very much. But there is a safe space. There is a forum for this kind of code, which is the International Obfuscated C Code Contest. And the objectives of the C Code Contest are to write the most obscure or obfuscated C program, to show the importance of programming style in an ironic way, as in, don't do this. See this? Don't do it. To stress C compilers with unusual code and find bugs that people didn't know they had, to illustrate the subtleties of the C language, and to provide a safe forum for poor C code. Now, here is an example from 2015. This is the complete source code to this program. Anyone, any C developers in the room? You want to just do a quick read through of that, tell me what it does? Or should we just run it? Like, YOLO, all right, bang, let's run it. We're going to run it through make it, and then we're going to run the program, and there it is. It's Flappy Bird running in a Unix terminal. Now here is another example from the Obfuscated C code contest. This one I particularly like. When you zoom in and do a kind of fine detailed code review, it's quite hard to see what's going on. So let's take a couple of steps back. We're going to just zoom out of this thing, because when you see the whole source code, it's a Mandelbrot set. It's a Mandelbrot set generator shaped like a Mandelbrot set. Now, this is JavaScript, everyone's favorite language for fun and profit. This is 1 kilobyte of JavaScript. If you copy and paste this into a text file and open it in a web browser, it plays chess. It doesn't draw chess, it plays chess. It has a chess engine, it has the Unicode codes for all of the individual pieces, it has logic, it even has this little drop-down menu at the bottom, because when one of your pawns makes it to the back rank in chess, you have to choose what piece it gets promoted to, and so that's probably about 20% of the code. Now, this was created by a guy called Oscar Toledo G, who is brilliant at writing these bizarre, wonderful, weird, artistic, esoteric computer programs. Now, in 1994, Simon Rasinkovich submitted this to the International C code contest. It's an empty file, 0 bytes. And he added a README file that says if you compile it with this particular C compiler, that C compiler, if you give it empty input, it produces a program that produces no output. So he argued that this program is a C program that prints its own source code. And they said, all right, and they gave him a prize, and they changed the rules. And from that year, your program had to be at least 1 byte. But this gets us on to the idea of something called a quine. If any of you has read Gödel, Escher, and Bach, there's a section in this book talks about a philosopher called William Ormond von Quine, who studied statements that refer to themselves. A quine is a program that prints its own source, and not just like reads the file off disk and echoes it. It's a program that procedurally generates its own source code. Now, I'm guessing that this is DevOps, so most of you are probably kind of Java developers, so we're going to have a go. We're going to write a quine in Java. So we got a public class quine, and we got a main method on there, and we need to, well, the first thing we need to do is we need to print a string, and the first line of our string needs to be public class quine static void, and okay, well then this needs to, yeah. We're going to get into difficulties. So what we need to do is we need to find the places where the language designers got drunk and divided by 0 and exploit the loopholes, because in Java we can use template strings. And so we can plug this template string in there, we can put in 2 system out print statements, and we can tell the template string, here is a literal quote, here is a literal new line, and by the way, we'd like you to use yourself as one of the formatting placeholders in your own template. And so this, in Java, if you run this, this prints its own source. Now in JavaScript, everything is a function and everything has a toString. So any function in JavaScript, you say this.toString, and there you go, you get your program back. In JavaScript 6, in ECMAScript 6, this is a quine. And I saw that, and I went, no, it's not, that's ridiculous. That's stupid. So I pasted it into the console in Chrome, and sure enough, it prints its own source code. Now, could you write a quine in HTML? There's a guy out there called Leon Bambrick, Secret Geek on Twitter. He does some really cool stuff, and he wrote a brutalist HTML quine. And I took that idea, I adapted it around a little bit. So here's the page, and this is the HTML source. Nothing terribly exciting going on in that. And what we're going to do is we're going to take the safety off and do things with a web browser you're not supposed to do. We are going to add a CSS rule that says display everything as a block, and suddenly, bang. Well, we can see our CSS rule. That's now appearing in the browser. We're going to go back in here. We're going to use some HTML pseudo elements before and after. HTML there. Now, /HTML, that's way off the bottom of the screen down here. Where would you put it? You've just told the browser, hey, when you finish drawing everything, draw this after the end. It's there, trust me, we'll bring it up in a minute. Then we're going to punch in a bunch more of these. We're going to put a white spacing pre-wrap formatting thing on that. And this page starts to approximate its own code. We are going to add a whole bunch more elements before and after to get opening and closing tags. We get to this point here. Now, we've got a link in this page. And we can use CSS to say, hey, if you see a link with an href, we'd like you to insert the content before that tells us where it points to. So we can drop that one in. And then the last thing we're going to do is just clean it up a little bit. We're going to put a margin, and we're going to override the height. And there it is. We have a web page that prints its own source. Completely useless, utterly pointless. But how many of you learned something you didn't know about web development from watching us put that thing together? Now, I want you to take a look at this, think about it for a second, and tell me what programming language do you think this code is written in? C. Do I hear C? because it looks like C. I mean, let's apply some syntax formatting. So we'll take out the comments. We got standard iota H, main char, a bit of a gnarly string literal in there, but okay, so that looks like C. Now we're going to apply Ruby source highlighting, and we're going to highlight the string literals. Which is it? Because that's valid Ruby. I mean, it's not nice Ruby, but it's valid. There's really only one thing we can do here. Let's compile it and run it and see what happens. So the listing for our program, here you go, nothing up my sleeves. Boom, there we go. We're going to run it through GCC. And we're going to run that, I'm going to build it, run it, and see what it does. And there it is, 1 warning generated. We're way past the point where we care about warnings here, folks. There it is. It prints its own source code. So now we're going to take the same thing, and we are going to run it through the Ruby interpreter. And it prints its own source code. And what the hell, while we're here, let's run it through Python and see what happens. And it prints its own source code. And any Perl developers out there? Any of you from the glory days of Web 1.0? Let's run it in Perl. There we go. It prints its own source code. And if you can find a C++ compiler that doesn't complain about main not having a return type, it'll print its own source code in C++ as well. This is a Polyquine. It is a program which prints its own source in more than one language. Now, take a look at this snippet of code here. Tell me if you recognize the programming language it's written in. Because we've got a system.console over here, so that's probably like a .NET or maybe a Java-y kind of thing. We've got an XML with an XSL transform namespace. We've got a for each with a console.log. That smells like JavaScript to me. We've got an Ada text I/O procedure for the Ada developers in the back row. Hello, we see you. We've got begin in block capitals, which means it's a serious business language like COBOL or SQL. And we've got Act 1, Scene 1, Enter Ajax, which that doesn't even look like programming, right? This is the Ouroboros quine. It is a Ruby program that produces a Rust program, that produces a Rex program, that produces a Scala program, that goes through 128 programming languages, and eventually it comes out as a Python program that produces an R program, that produces a RAT4, that produces an RC, that produces the original Ruby program again. That's not the cool part. The source code to the Ouroboros quine looks like this. That's not the cool part. If we zoom in on the bottom corner here, this thing is future-proof. It's got maintenance hooks in case they need to. That's not the cool part. All 128 of those languages you can install by doing apt-get on Ubuntu Linux, which means there is a GitHub Actions continuous test deployment thing for the Ouroboros quine that runs all 128 languages and makes sure all of them come out green. Now that's the cool part. But let's backtrack a little bit. Now, buried in among the Ada and the COBOL and the JavaScript, we had an Act 1, Scene 1, Enter Ajax. That is a programming language called Shakespeare. Now, Shakespeare is an esoteric language. The entire programming language is a work of art. It was designed to let you write computer programs that look like plays, specifically look like plays written by William Shakespeare. Variables in Shakespeare have names. You declare your scene, you introduce your characters, this puts the variables in scope, and then they talk to each other. And if you insult a character, the value in that variable is decremented. And if you compliment a character, the value in that character is incremented. Hello world. Romeo, a young man with remarkable patience, meets Hamlet, the flatterer of Anderson insulting. Act 1, Scene 1, enter Hamlet and Romeo. And Hamlet says to Romeo, "You lying, stupid, fatherless, big, smelly, half-witted coward. You are as stupid as the difference between a handsome, rich, brave hero and thyself. Speak your mind." That prints H. Romeo goes on to say, "You are as brave as the sum of your fat, little, stuffed, misused, dusty, old, rotten codpiece." It goes on for several pages, much as Shakespeare himself did. And at the end of several pages, it prints H-E-L-L-O, world. Shakespeare is not noted for brevity, either as a playwright or as a programming language. Now, let's take a look at another example. Anyone recognize this programming language? It's one of my favorites. This is the programming language called whitespace. In whitespace, all of your operators and keywords are combinations of spaces and tabs, and everything else is a comment. So if you ever want to hide a program inside another program, white space is a wonderful way of doing it. Just tell people that's your house style when it comes to indentation. Now, there is a programming language out there called Chef. And Chef is designed to write programs that look like recipes. Now, this is the canonical Hello World in Chef. It involves 72 grams of beans and 101 eggs and 108 grams of lard and 33 potatoes, and you're kind of looking at that going, I don't think I want to eat Hello World. That does not look nutritious. And so a guy called Mike Wirth set out to create a Hello World in Chef that was actually an edible recipe. And he created this, the Hello World cake. Now, if you run this, exactly this text through the Chef interpreter, it prints Hello World. But if you run it on your kitchen, you get a chocolate cake with chocolate sauce that you can give to your guests who have no idea that they're eating a computer program. And that's the thing about esoteric languages, which I love, is you can have programs that don't even look like they are programs. We are going to see now, how do you square a number in the programming language called Pete? That is how you square a number in Pete. Pete is a graphical programming language. The instruction set in Pete is based on moving from areas of one color to another. This is the color palette that it uses, and the instruction pointer starts in the top left corner, and it starts off moving horizontally. So we go from there to there. When we cross from light blue to dark green, input a number. Get the user to input a number. Then when we hit black, we turn right. When we cross from green into red, that says duplicate the value on the top of the stack. We cross from red into yellow, that is a multiply instruction. We cross from yellow into red, that says output the number on the top of the stack. We cross the white is a no-op. We hit the edge, we are going to turn right. We are going to follow blue until we end up with black on all sides, and that's it. Halt. The program is now finished. Now, this is Hello World in Pete. But you could also print this out and hang it on the wall, and people just think you liked impressionist art. Like, they would have no idea that this was a computer program. Now, we have this habit at things like DevOps and software conferences where somebody will, they will do a talk, and then at some point in their talk, they're going to go, right, we're going to do a live demo. And everyone goes, oh, live demo, because demos are exciting, right? Because demos might go wrong. And we, as an industry, we do not like things that might go wrong. You know, if someone's like, hey, watch this, I'm going to deploy to production, you don't want to be sitting on the edge of your seat excited. You want that to be mundane. You want it to be boring and repetitive and automated. And we have this expression in our industry. We talk about snowflake servers and snowflake processes. And we say, no, don't check that server, it's a snowflake. What do you mean? If you put Windows Update on it, no one gets paid. You know, we don't know how it works. We don't know why it works. We don't have another one. It's completely unique in the universe. Don't even move the mouse. We don't know at this point. You know, snowflake is a derogatory term. We don't like this idea of uniqueness. We don't like things that can't be trivially reproduced. But when you watch a live demo, when you watch a performance, when you go to a show or something, you become part of an experience. If you pluck a snowflake out of a blizzard, every snowflake in nature is unique, and you watch it melt on your hand, and you are the only person who was ever going to be part of that. And that's what makes live performance so mesmerizing, is no matter how many people are recording it on their phone and posting it on Instagram later, being there, being part of that, that's something that can't be replicated. This is the London Philharmonic Orchestra performing live at the Albert Hall in London. And the guy up there in the black t-shirt underneath the screen, that is Sam Aaron. And Sam is the creator of Sonic Pi, which is a musical programming language designed for live performance. Now, Sonic Pi is wonderful. Sonic Pi was designed to teach kids to program by giving them outputs which are immediately accessible and engaging, and it has found a niche among live performers, DJs, algorave musicians. We're going to do a little demo. So Sonic Pi, by default, when you fire it up, you say play A3, and it plays A3. Now, Sonic Pi runs all of its statements in parallel unless you tell it not to. Just think for 1 second what would happen if Java did that. If you want it to do things one after the other, you have to tell it to sleep. You have to introduce delays into your program code. But this is a Turing-complete, fully-fledged programming language. We can take a bunch of notes, and we can say, right, 16 times do end, we got a loop syntax, dung, dung, and we get this fairly unexciting and funereal loop. spice things up a little bit. So we're going to say crank it up to 244 beats per minute. That's nice. Ding, 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 ding. And now we're going to go in, and what we're going to do is we're going to replace the synthesizer noise it's using. Instead of the sine wave, we're going to use a thing called textsource. Yeah, that's sounding kind of fun. But where it gets really fun is where you start interweaving logic with the code which actually generates the music. So we're going to take our 16 times loop here, and we are going to call it a live loop. Now, a live loop allows you to synchronize different parts of your program so that they play in synchronization. And what we are going to do is we're going to plug in here another live loop that is going to just play an open symbol and then a closed symbol sample. So we're going to drop that one in there. That's going to sleep, and then on the 16th beat, it's going to do this. Now I'm going to drop in a kick drum and a snare drum from a buffer that I created earlier, so we're going to grab that lot, come over into buffer 0, paste that in there. Now we don't have to restart the program at any point here, it just keeps on running. And it keeps in time, and keeps in sync, and we can mess with it while it runs. So we're going to introduce a counter variable. And we're going to say, right, I is going to go round and round in the loop, and each loop I is going to count to 16. And if I is divisible by 3, we want you to play the C4 instead of A3, play a different note. And if I is divisible by 5, we want you to play this note instead of that note. And some of you might be seeing which popular interview algorithm is being implemented here in the medium of music. And if I is divisible by 15, we're going to drop down and play the low G. And so what we've got here we have FizzBuzz implemented live in Sonic Pi as a loop with the 15, 5, 3 factors. This is called the FizzBuzz riff, and we're going to come back to that in a moment. Now, we have talked about all kinds of cool and awesome and interesting things that other people have done and that they've shared with the world and put on GitHub so we can go and play around with their stuff. But I want to close out today by talking about something I did. Now, some of you may be familiar with the trope of the Rockstar developer, because if you go on any of the IT job sites and you look for Rockstars, you'll find they're looking for an incredible Rockstar junior web developer, or a Rockstar senior front-end developer, Rockstar JavaScript and Node.js developer. We need a Rockstar senior Java software developer with a passion for developing. And a couple of years ago, about 2018, a guy called Paul Stovall went on Twitter one day and he said, to confuse recruiters, someone should make a programming language called Rockstar. And I saw this tweet, and I had this experience. I had a moment of divine revelation. Suddenly it was clear why I was put here on this earth, because the part of my childhood that I did not waste playing around with Amstrad 6128s and fractal geometry and messing around with computers, I spent listening to heavy metal music by men with big hair and tight trousers, and I thought that's what the world needs. We need a programming language called Rockstar where all of your programs are also 1980s heavy metal ballads. Now, there are a couple of things you need to understand about the design process for the Rockstar programming language. One, it was invented as a joke, and two, it was invented in a bar. There are reasons that will become apparent. I sat down, I was in Sydney, Australia, and I was meeting some friends in a bar. They were running late, and I had my laptop, and I had a beer. I was like, I wonder, and it just started out like, can I write a spec? Like a parody language specification that just nicks all kinds of lyrics from heavy metal and rock songs and puts them in. Now, I spent a bunch of time in my career working with Perl. I spent a bunch of time working with Ruby and VB script. And so I've found lots of languages that use sort of English-like syntax. And so I sat down and I banged out a draft proposal for a dynamically typed Turing-complete programming language for creating computer programs that are also song lyrics, heavily influenced by the lyrical conventions of 1980s hard rock and power ballads. Now, Hello World in Rockstar is just say hello world. We want to set the bar very low for the sort of the intellectual threshold for becoming a Rockstar developer. But maybe you don't feel like saying it today. Maybe you want to scream it, or you want to whisper it, or you want to shout it. That's all fine. That's valid. That allows you to get your emotion into the programs that you're writing. Now, variables and assignment is a problem, because we like to argue about the correct way to name things. Do we have, well, int x equals 5, all right, and var my underscore string equals hello world, and var the message equals devox rocks. Now, I decided very early on, about halfway through my first beer, that Rockstar was going to be dynamically typed and it wasn't going to have semicolons. Because, if Ruby can get away with that, then hey, we can get away with that too. Now, equals looks a bit like maths, and maths tends to scare Rockstars, so I was like, we can't have maths in this. X is 5, that'll do. My string is and hello world, the message is Devox rocks. But then it's like, well, we've got this underscore and this weird casing thing. You ever had that argument with your team for like 4 hours about should you use camel case or Pascal case or kebab case or underscore left-handed chainsaw Hungarian case? And I saw a talk Douglas Crockford gave a couple of years ago where he said, these arguments are stupid because really what we want are variable names with spaces in them. Well, when you're inventing a programming language in a bar as a joke, you can do anything you want. So Rockstar has variable names with spaces. Now, it's not a complete free-for-all. There are some grammatical rules around it. There are simple variables, which are just identifiers that aren't keywords. There are common variables which have to be prefixed with my, an, your, a, the. And there are proper variables which have to have initials. So you can have variables called Dr. Feelgood and Black Betty and Billie Jean. Now, when it came to initializing literals, a lot of languages, you assign a lot of numbers when you set up your program, screen width and height and all that kind of stuff. And numbers aren't very rock and roll. There's that Billy Ray Cyrus song where he sings the phone number, and that was one of history's horrible mistakes, and we're not doing that again. And I thought, how can you initialize numeric values without having to put numeric literals in your code? And I thought, what if we take the lengths of the words on the line, modulo 10, and treat those as decimal digits? And so this gives us a way of initializing 3, 5, and 100. So we're on the way to being able to write FizzBuzz so we can start interviewing Rockstar developers. Now you can do it with floating points as well. In C#, decimal pi equals 3.141592. In JavaScript, we have var pi equals 3.1415, and after that you should probably stop counting because you're way off the end of the precision. In Rockstar, my heart was ice, a life unfulfilled, waking everybody up, taking booze and pills, is how you put pi in a variable. 3, ice, dot, 14159265535. Arithmetic. You got to have arithmetic. Now, you listen to people talk about numbers. They're like, how much is the bill? Oh, it's the price with the tax. How much is the, oh, it's the total without the tax. The quantity of the product, we talk about the distance over the time. Or we can talk about a girl with a dream, a man without a face, the wings of the night, a whisper over the water. We needed comparison so you can do loops and operators. Your love is a lie, true or false? The whiskey ain't the answer, true or false? My heart is stronger than steel. My soul is weaker than water. My will is as strong as a lion. Your lies are as low as a snake. This is really getting somewhere. So I order another beer. I'm like, right, how are we going to do functions? And I think, well, if you describe the technique of doing arithmetic modulus by repeated subtraction, you say something like, all right, so modulus, it takes a number and a divisor, and then while the number is as high as the divisor, you're going to subtract it, so you put the number, take off the divisor, put that back into the number, and then the blank line here, that's how you terminate loops in Rockstar. That was a horrible mistake. We'll get back to that in a minute. And then at the end of the loop, once you've finished looping, you give back the number. Or midnight takes your heart and your soul. And while your heart is as high as your soul, you put your heart without your soul into your heart, and you give back your heart. So I put this on Twitter, and I stagger back to my hotel, and I go to bed. And I publish the spec up on GitHub, and the internet finds it. And the internet goes, ooh, a shiny thing. And it makes the homepage of Hacker News. And it makes the homepage of Reddit. And people start, Cory Doctorow's Boing Boing, they did a write-up about it. It started getting comments. People on Reddit were saying nice things. Like, have you ever seen people on Reddit saying nice things? Like, I love it, this is funny, pure genius, the docs are hilarious, shut up and take my money. And then I got an email from Classic Rock magazine, which has nothing to do with esoteric programming languages or computers. It's a real sensible music magazine that interviews real musicians, saying, what is this Rockstar thing we're hearing about? And so they did an article on it. And I made it into Classic Rock magazine for inventing a programming language in a bar. And then it got weird. Because people started filing GitHub issues against my spec. And I sort of reached out to them, and I was like, why are you filing issues? And they're like, oh, the spec has, this bit here has undefined behavior. I'm like, so? And they're like, my Scala interpreter doesn't work. I'm like, you're what? And like, yeah, somebody built a Rockstar interpreter in Scala in a weekend for fun. And somebody else built a Rockstar to Python transpiler, and somebody else built a Rockstar interpreter in Rust. And I was just blown away. And I was like, I want to do that. I want to know how to build interpreters for my programming language I invented in a bar. Now, I'd done compiler engineering at university, but that was a long time ago, and a lot has happened since then. So I took a couple of weeks off, and I dived into how do you build interpreters. How do you build a parser for a joke programming language? Now, the kind of fun part, about 80% of it just worked. Some of it was kind of daft, and there's a couple of things that if I wasn't inventing languages in a bar, I'd have done differently. But most of it, the first spec was implemented straight off. Now, I did mine in JavaScript. And I did mine in JavaScript for one very, very good reason. I wanted to be able to run it in a web browser so that anybody, anywhere in the world, anytime, could get out their laptop or they could get out their phone. They could go to codewithrockstar.com, and they could type their program in, and they could click Run. Because if you do that, and it works, you are a Rockstar developer. Everybody in this room can be a Rockstar developer right now. Now, when you put stuff online, I wanted to do a little bit of branding, and I was looking around, I wanted a sort of a heavy metal logo for this thing. So I looked at Judas Priest and Iron Maiden and Metallica, and none of that really kind of spoke to me. And eventually, I found my inspiration for Rockstar's logo type. And this logo is recycled from Microsoft Consumer Products' actual logo 1980 to 1982, which they aren't using anymore. And so I've recycled that, and so all those lovely angular logo types are still existing. Now, you can go to that web address right now. I have with me today a supply of certified Rockstar developer self-adhesive certificates that you can put on your laptop, and next time you're in a meeting and someone says, oh, we need a Rockstar for this one, you're like, hey, look, I'm certified. So come up and see me at the end if you want to grab one of those. And we are going to close out now because the ultimate, the acid test of Rockstar as a programming language. We've seen the Hello World that's actually a chocolate cake. And we've seen the Pete Mondrian Hello World that you could hang on your wall and nobody would know it was that. And so what we're going to do now is I'm going to perform FizzBuzz for you. And I want you just to listen to this and tell me if you found this on the B-side of a Meatloaf record from 1987, would you know you were listening to FizzBuzz? Or would you just think, yeah, this Meatloaf song's kind of a little bit cliched, but it's probably all right?
Takes your heart and your soul, and while your heart is as high as your soul, put your heart without your soul into your heart. Give back your heart. Fire is ice, heat is water, till my world is desire. and midnight taking my world. Hate is nothing. Shout fizz buzz and take it to the top. Midnight taking my world. Fire is nothing. Shout fizz and take it to the top. Midnight taking my world. Hate is nothing. Save us and take it to the top. Whisper my word.
Thank you very much, Devox. Thank you. And yes, I do have stickers. Come and find me afterwards. I think some of us are going to watch Top Gun, and some of us are probably going to go and have some beer. I'm going to go and have some beer. Although I have seen Top Gun, and it's brilliant. So if you haven't seen it, go and see Top Gun, and then come and have some beer.
I think that's the plan. Yeah. Great. Thank you very much, Dylan. Thank you. It was amazing.
My pleasure.
Great. That was it, man. You can finally go to the movie. You still have 20 minutes. Make sure you get your jackets at the cloakroom. And I would say get some popcorn and enjoy Tom Cruise with Top Gun. Have a good one.